Good afternoon, everybody. My name is Sergey. I'm coming from TU Berlin. And today I would like to share with you our work in progress in the area of unsupervised data quality validation on dynamic data. With this work, we want to bring a challenge from the data management community on establishing trustworthy data pipelines through validation of the quality of the input data. But before we go deeper into the approach and the experimental setup, I would like to start with a few motivational examples. Imagine a data engineering team at a retail company that maintains a search engine for products. They regularly collect, pre-process, and ingest product data from web crawls, key value stores, or data pipelines from other teams in order to index this data and keep the search engine up to date. If another team introduces errors in their data pipelines, issues like missing values or wrong encoding might lead to the product not being indexed correctly. As a result, products might end up in the wrong category or not appear in the search feed at all. As another example that is more relevant to machine learning, imagine that you have a machine learning pipeline that is deployed to a servant system. Here is a simplified scheme. Data from heterogeneous sources pass through data gathering and data preparation phases, and then is used for model selection and training. The deployed model is continuously monitored with the KPI dashboards or alerting systems. It's then exposed via different interfaces to the end user. Errors in data might lead to software exceptions and system crashes of the deployed pipeline. And in case the servant system or the pipeline itself are robust to these errors, for instance, when the missing value imputation mechanisms are in place, the errors would still most likely deteriorate the model's predicted performance. So in general, we assume the errors in data arise either from the data generating process, where we are initially collecting the data of the unsatisfied quality, or from data pre-processing, where we are receiving the high quality data and corrupting it in any way in the data pipeline. In the real world applications, these issues become even more pressing due to several reasons. First, data comes from heterogeneous sources with diverse standards for data quality. For example, part of the data might be coming from relational databases with strict integrity constraints, whereas another part might be ingested from web tables and crawls, key value stores, or simply CSV files with little to no constraints on data quality being specified. Secondly, different use cases might vary in requirements for data quality, making the concept of data quality very subjective and application specific. We see two main lines of research that address these issues from the data management perspective. The first area is error detection, which aims at classifying data on very high granular cell or record level as correct or erroneous. Various examples of error detection algorithms consider the data erroneous upon violation of a rule, of a pattern, upon the presence of outliers or duplicates. Another research direction is data quality validation that aims at assuring that the data is of accepted quality. Examples of the solutions in the area are the Amazon's DeepCube library that enables declarative data unit tests to monitor whether the data passed this test or not, the TensorFlow data validation toolkit that checks for the violation of data schema, or the data linter that provides data lints to indicate the violation of best practices while working with data, similar to code lints in software engineering that define best practices in programming. All these solutions have something in common. They require either domain expertise in the form of rules, patterns, constraints to define data quality, or labeled examples for the algorithms to learn what records are of acceptable data quality automatically. These requirements bring several research questions. First, what if the domain knowledge is incomplete and even the expert doesn't know for certain what data is of high quality and what not? Or what if monitoring a data stream by the domain expert is too costly or too time-consuming? Another question is, what if the data change over time and the state of high quality as of yesterday is not the same as the high quality of today? In short, we need a solution that does not require domain expertise in any form and can adapt to the changing data. To limit the scope of this problem, we looked at the common real-world use cases and made the following observations. First of all, we work with the tabular data that comes regularly in batches. For example, weekly data ingestion in our retail company use case. Then we consider the historical data to be of acceptable data quality. This assumption is critical. It means that at the time t, we allow ourselves to use the data from time step 0 to time step t-1 as the training set that helps us model the data of high quality. If this assumption seems counterintuitive, let's get back for a moment to our motivational examples. For the retail company, products that are placed in the wrong category or not appearing in the search results at all lead to negative customer reports or low service ratings. For the machine learning service system, errors in data lead to system crashes with immediate notifications to the DevOps team, or to the model performance degradation, leading to alerts by the monitoring system. To put it simply, should anything bad happen, we would have already learned about it, as it affects business KPIs that are usually very carefully monitored. Another note is that this assumption also brings a major challenge to the setup. By considering the historical data to be of acceptable quality, we do not get any negative examples, meaning that we don't have labels for the second class and simply cannot consider it a binary classification problem. As for the last assumption, we consider that in case errors occur, they most likely affect a large fraction of the batch. For instance, the missing values or wrong encoding will affect the whole batch of data rather than a single record or a single cell. So these assumptions let us try out the following approach. For every attribute of the incoming data batch, we compute several simple descriptive statistics, such as completeness, the number of distinctive values, mean or standard deviation for the numeric data types. We record these values over time. And before the new data arrives, we build an estimate of the statistics for the next upcoming batch. When the batch becomes available, we compute the actual statistics and compare them against our estimate. In case of significant mismatches, we raise an alert to the end user. Let's briefly take a look at the example data table. Here we have 4 attributes, 2 numerical ones, salary and the extension number, and 2 attributes that are represented as strings. For every attribute, we compute the following metrics: completeness, the fraction of not null values, and the approximate number of distinctive values. For numeric attribute, we additionally compute the mean, standard deviation, as well as minimum and maximum values. So in this particular example, we would compute 16 metrics in total. As for the evaluation scenario, we use the following scheme. We take relational data that consists of chronologically ordered partitions. For every partition T, we use the previous partitions from time step 0 to time step T-1 as training data for our model. And then we randomly choose either the partition T or its corrupted version T star, show it to the model, and let it decide whether the batch is of acceptable data quality or not. We then use binary classification metrics such as accuracy, F1 score, or the area under the ROC curve to evaluate how well the model performed. We use two real-world datasets that have both the dirty and the clean versions of the data, and three real-world datasets without ground truth, where we generate errors synthetically. The example of the errors are missing values, explicit or implicit, numerical outliers, or wrong encoding. We randomly select a fraction of the batch and replace the actual values with the corrected ones. For the synthetic datasets, we keep the fraction of errors equal to 30%. In our experiments, we created two prototypes. In the first prototype, we treated every recorded metric as univariate time series. For every attribute of a batch, we were calculating descriptive metrics. For every timestamp, we were estimating the future value of that metric by applying time series forecasting methods from the ARIMA family, such as autoregressive models, moving averaging models, as well as the Facebook profit forecasting library. When the actual value became available, we were comparing the estimate and the actual value by using the outlier rules, such as Z-score, where the value is considered to be an outlier if it goes beyond 3 standard deviations from the mean of the estimate. Confidence interval, where the value exceeds the 95% confidence interval boundaries, or percentage deviation, where the value deviates from the estimate more than K%. We were raising alerts or classifying the batch as erroneous in cases when a critical mismatch happened. As we also needed to consolidate the output of multiple models that were trained on every metric, we also applied the aggregation rules. For example, we were classifying a batch as erroneous if at least one model classified the batch as anomaly, or at least K models did. We also tried the majority voting and the agreed by all the models approach. Although a combination of a forecasting model and the outlier rule performed well on the metric level, so on the level of the univariate time series, it showed the random guess performance after applying aggregation rules, as we had to consolidate the decisions that the model made about every metric of every column of the batch into a single output, whether the whole batch is considered to be of acceptable quality or not. As we derived the aggregation rules to be the main bottleneck of the first prototype, we decided to focus on another family of algorithms, novelty detection. Instead of treating every metric as a univariate time series, we treat all the values of these metrics per timestamp as a multivariate record in the training set. So on the one hand, this approach discards time as a feature. On the other hand, it eliminates the need for aggregation rules because each record is considered a multivariate data point. So the rest in principle is analogous to the approach I described earlier. As an example method from the novelty detection family, we took one class SVM as two baselines, which chose TensorFlow data validation and statistical testing. The first solution uses the training set to infer the data schema. The second solution performs statistical testing with the null hypothesis that the training data and the current batch of interest belong to different data distribution. This approach performs a series of univariate tests, one per attribute of the batch, and aggregates the results. Then later, including the Bonferroni correction from multiple tests. Below are the results of the experiments comparing the AUC score. Our approach reaches 91% on average across 5 datasets, compared to 64% for TensorFlow data validation and 50% for statistical testing. Further experiment analysis showed that the baseline solutions have classified most of the batches as erroneous, most likely due to the presence of new, previously unseen values in the attribute. As for future work, we consider the following directions. First, we are trying out smaller error fraction. As of now, we were considering a fixed fraction of errors equal to 30%, and we don't know yet how well our prototype performs when the fraction of errors is smaller. Then we're trying other novelty detection algorithms such as isolation forest or k-nearest neighbor to see whether there are more attractive candidates for our solution. We also need to consider other baselines. One of the examples is the HPI Metanom project, a data profiling platform. And we're still looking for other real-world data sets, especially the ones that have ground truths with respect to the data quality. To summarize the talk, I would like to address several points as a takeaway message. Data quality validation is crucial for establishing trustworthy data pipelines. The most challenging cases are the ones where domain expertise is incomplete and data change over time. And as it turned out, collecting simple descriptive statistics over the data and analyzing them with novelty detection methods makes it possible to distinguish critical errors in data, does not require domain knowledge at all, and adapt to the changing data. And here's the QR code for our paper. By that, I would like to finish my talk. Thank you so much for your time and take care.